Time for our second talk. We have Pierre-Guy Plamondon, and a very warm welcome to you. And I really appreciate your consent to come here and give lectures. I hope that this is also around the same theme of categorification and representations and cluster algebras, connections to them. So I have to know about you, and I'll be able to get a better introduction about you next time.
Thank you very much. And thank you for the invitation. In fact, this is my first time in India, and I'm very happy to be here in this beautiful institute. And as you said, my lectures will be on a very similar theme as the one from Bernhard this morning. I will talk about categorification of cluster algebras. The title of my lectures, so the general title is Generic Cluster Characters. And so generic cluster characters is a term that will only appear towards the end of my lectures. It will be more or less split into 3 chapters. The first one, I want to talk about indices in cluster categories. This will require me to talk a little bit about projective presentations in module categories. In the second part, I want to talk about cluster characters. And these are a generalization of the Caldero-Chapoton maps that were introduced by Laurent in his lectures. And in the third part, I want to talk about, finally, generic cluster characters. And approximately, the first 2 chapters will each take 1 lecture, and the third chapter will take up the 2 last lectures. But this is approximate. Let's see how it goes. So let's start with the first section. And before doing anything more, I want to start with an example. So 1.1, an example. And as an example, I want us to construct the cluster category of the Kronecker quiver. So the Kronecker quiver is the quiver with 2 vertices and 2 arrows. And if I impose that it's without oriented cycles, then there's only one choice up to a change of orientation. So let's call these 2 arrows A and B. This is the Kronecker quiver. And I want to construct the cluster category. Of this Kronecker quiver. We've just seen in Bernhard's lecture that the cluster category is defined as an orbit category of the bounded derived category. The bounded derived category of the modules over the path algebra KQ. And we take the orbit by the action of a certain functor, which turns out to be the composition of the Ausländerräten translation with the inverse of the suspension functor. So we want to construct this. In order to do this, we need to know what the bounded derived category is. But we've seen that the indecomposables, the indecomposable objects in the bounded derived category are complexes concentrated in 1 degree, where in this 1 degree we have an indecomposable module over KQ. So R in bijection with complexes, well, I should say R complexes concentrated in 1 degree with an indecomposable KQ module in this degree. So in order to know the bounded derived category, what we need to know really is the module category over KQ. So let's describe the module category over KQ. We are doing right modules, and we are, as in Bernhard's lecture, composing arrows as we would be composing morphisms, so from right to left. This choice of convention means that modules over the path algebra KQ are the same thing as representations of the opposite quiver. So what we really want to classify are indecomposable representations of the quiver whose 2 arrows go from right to left. Now, what I will now show you is what this classification is, without proving that this is a classification of indecomposables. I'm doing this because this will serve as a running example throughout the lectures, and it's good to have one example where we can see everything and compute everything that is going on. So let's start. Let's start here, maybe. Let's look at indecomposables over the opposite quiver. So the opposite quiver has arrows going from right to left. And there's one obvious indecomposable representations that goes like this. It turns out to be the projective P1, if I follow the notations of Bernhard's lecture. There should be a second projective. That should be P2. So I will write in detail what this representation is. It has dimension vector 2, 1. And the maps given as matrices are as follow. Now you can check that this is an indecomposable representations in any way you like. This is a very small example, so you could try to decompose it and prove that you cannot do it non-trivially. You could compute its endomorphism ring and you would find that it's local. It's actually isomorphic to the base field K. So whatever method that you choose, you will find that this is an indecomposable module. And I will give you now a list of other indecomposables. Here's another one of dimension vector 3, 2, with morphisms given as follow. So again, I'm claiming that this is indecomposable, but you could prove it by hand. Yes, you could. What I would do was try to compute its endomorphism ring and prove that it is local. Again, this is not the only way to do it, but whatever you choose. And in general, yes, you see that these all look alike in some sense. Yes, I always have a dimension vector of n+1 n with some maps that look like the identity on top and 0 above, or 0 on top and the identity below. And this turns out to be general. If I give you the following representation, this is indecomposable. And again, this is, even though this is more general, n can be any integer, this you can prove by hand. Now there are natural morphisms between these representations. For instance, this representation P1, should have said that this is, I've said it, but I did not write it down. This is the projective at 2. Now this projective P1 can be embedded in P2 in several different ways, yes? All you need to do is embed this copy of K into k square. And you can do this in various ways, but there's a basis of ways you can do this. You either embed k into the first copy of k here, or you embed k into the second copy of k here, and you can take any linear combinations of those two embeddings. These two embeddings are irreducible maps, which have been defined in Laurent's talk. So I'm going to write two arrows that correspond to these two irreducible maps that are linearly independent. Now, it turns out that there are two linearly independent irreducible maps from this representation to this one as well. I'm not going to write them down, but you can do this as an exercise and describe them precisely, and so on. So here we have a family of indecomposable representations. I'm only taking irreducible maps. So maps that, from this one to this one, you mean, yes. There are more than two, but two of them form a basis of the space of irreducible maps. Yes. Yes. I mean, even here, I'm only drawing two arrows because they correspond to two embeddings. But if I take any linear combination of these two arrows, then I get another map, another irreducible map, in fact, from this one to this one, yes. So I have a full space, two-dimensional space of irreducible maps. And this is going to be true as well here. I only write two arrows because I just want a basis of these maps. Between this one and this one, yes. I'm not sure what you want me to explain, but I could say that, I mean, there are indeed maps from this to this, yes, because you can embed this copy of k in various ways into k to the cube, yes. But you have a basis for these various embeddings given by saying that k is embedded in the first copy, or in the second copy, or in the third copy, yes. And any linear combinations of these give you an embedding. However, these are not irreducible because whatever you choose, you can decide to go through this one, yes. But in order to view this, you need to make these maps explicit. Yes. But once you've done this, you will see that no map from this guy to this guy is irreducible. And then once you've done this for this, just this here, you can repeat the argument using the same ideas for any n, yes. And this will give you an infinite family of indecomposable representations and irreducible maps between them. It turns out that for every triangle that you see here, you get an almost split sequence or Auslander-Rayton sequence. I'm not sure which terminology. You use both. Okay, I will use both as well. In here, you have this representation. And since you have two irreducible maps here, I will have to draw them both. So I will have two copies of this representation in the middle term of this sequence. So when I write a square, I mean direct sum of this module with itself. And then I go into this one. And this is an almost split sequence. And of course, I've done this with this first triangle, but this is true for any n, yes. So you have an infinite family of Auslander-Rayton sequences that you've constructed in this way. Okay, I started with the simple at 1. Dually, I could have started with the simple at 2. So I will go on the other side of the board and leave me some space. And I've written the arrows in the wrong direction. Yes. So here is an indecomposable module. This one is obviously indecomposable. It's of dimension 1. There can be no trivial submodule. This one is not projective, but it's injective. A dual notion to the notion of projective module. So, my index should be 2. Yes, thank you. Okay. And then everything I've done here transposes on this side in a dual fashion. So I will not say more about it. I will just write down some indecomposable modules. They will all have dimension vector n plus 1. And I think you can guess what the morphisms associated to the arrows should be. But I will draw the first few ones in any case. So here is one. It turns out that this one is the injective at 1. There you go. Okay, dimension vector 2, 3. And so on for a general module of dimension vector n plus 1. And you put the identity on one side and 0 on the other for the morphisms. And in a similar fashion, on this side, there was a space of dimension 2 of embeddings from this P1 to this P2. On the other side, dually, there's a space of dimension 2 of projections from this I1 onto this I2. So I will have a space of irreducible maps of dimension 2. Yes, I could either say, take the first copy of K, send it to K, and the second send it to 0, or vice versa. Or take any linear combinations of those two projections, and so on. So here I found another infinite family of indecomposable representations, another infinite family also of almost split sequences. But that's not all indecomposable representations. There are some missing. And what I will not show today is why the list I will give is complete, but let me give you what indecomposable representations are missing. So for any, if I take any lambda non-zero scalar in my base field, which I should have assumed right from the start to be algebraically closed. So I will do this now. So K is an algebraically closed field. At some point in my lectures, K will be the field of complex numbers. But for the moment, I don't need this. Okay. Let's give some space. Yes. And now for any lambda, here's an indecomposable representation. I put lambda on top and 1 at the bottom. It's easy to prove that the endomorphism ring of this representation is the field K itself, so it's local, so this representation is indecomposable. Whatever lambda you choose. And if you change lambda, you get another representation which is not isomorphic. So here I've gotten a family of an infinite family of indecomposable representations. And you can build some others of dimension vector n in general. So then what you do is you put the identity on the bottom and you put a Jordan block on top with eigenvalue lambda. Yes. And it turns out that there's one irreducible map up to scalar from this representation to this representation. It's an inclusion. And there's also an irreducible map from the bigger representation to the smaller one. It's a projection. So maybe to differentiate between my arrows, I will circle my representations, no? And you can do this more generally if you have for any integer n, you will have an indecomposable representation of dimension vector nn, and the morphisms associated to the arrows are a Jordan block of eigenvalue lambda and size n on top, and the identity of size n at the bottom. And you get irreducible maps going up and down. Okay. So this here, my field is algebraically closed, so I have infinitely many values of lambda, so I have infinitely many diagrams of this type going up, yes. Infinitely many families of infinitely many indecomposable representations of dimension vector nn. But it also works for lambda is 1. 0, yes. I want to keep this one separated because if you take other quivers of affine type, you will have different family. I want to keep this one separate. And you also have another family where you put a 1 on top and a 0 at the bottom. Yes. So if you look at all these families here, with these two I have one upgoing tube for every scalar, and I have another one here, which you can view as infinity on the projective line. So here I have a P1 family of tubes. Now, for each of the representations that I've drawn on the board, you can check for yourself that they are indecomposable. This is not such a difficult exercise. The difficult exercise is to prove that all indecomposable representations are on the board at the moment. Yes. So maybe I write this as a theorem. All indecomposable representations up to isomorphism of the Kronecker quiver appear in the picture. And also, Laurent in his lectures has defined what the Ausländerraten quiver of a quiver is. Yes, it's a quiver whose vertices correspond to indecomposable representations and whose arrows correspond to a basis of the space of irreducible maps between them. And part of the theorem is also that what I've drawn here is the Ausländerraten quiver of the Kronecker quiver. So in this picture, you have all irreducible maps and you have all indecomposable representations. Now, this is a description of the module category of the path algebra of the Kronecker quiver. What we're interested in is the cluster category. So in particular, we need the bounded derived category. So now let's describe the bounded derived category. Recall that the indecomposables in the bounded derived categories are just indecomposables in the module category, and you use the suspension factor to construct complexes concentrated in 1 degree using these. So all you have is infinitely many copies of the module category inside the bounded derived categories, and this describes all indecomposables. So let's give a more schematic picture of what I've drawn here. So I've started with the 2 projectives, and then I've constructed an infinite family of indecomposables of dimension vector n plus 1n. Then in the middle, I've put an infinite family of tubes. A P1 family of tubes, which I'll draw like this. And then on the right, I've drawn an infinite family of representations of dimension vector n plus 1, ending in the injective modules. So this is mod KQ. And the reason I've put them in this order is that there are morphisms from people in here to the people in here and here. There are morphisms from the people in here to the people in here, but there are no morphisms going backwards. This is also something that you can prove. Now there's also, if I shift the module category, I get a new copy of it. So this is mod KQ, to which I have applied the suspension functor. And if I shift it again, I get a new copy, and so on. This is the second power of the shift applied to mod KQ, and so on. And of course, the suspension functor is invertible, so I could go backwards as well. So I have a copy here. This is sigma minus 1 applied to mod KQ, and so on. So far, so good. So here I have a description of the bounded derived category. Now, what do I want? I want the cluster category. And the cluster category, recall its definition. It's an orbit category where I decide that tau, the Ausländerräten translation, and the shift become equal. Now, what is the action of tau on this picture? The Ausländerräten translation is just going 1 step to the left. Okay. What is the action of sigma? Well, the action of sigma, you see it on the picture here. So if you start here, sigma of this point is here. It's a translation, yes. And then sigma again, and so on. So if you choose any point in here, if you apply sigma, you get here, and you get here, and you get here. It's just a translation. So these are 2 automorphisms. And when I declare that they become equal in the cluster category, what do I say on this picture? I say that if I start, say, here, so these are the projectives. If I apply sigma, I get here. And then I apply tau minus 1, so I go 1 step to the right. Yes? then in the orbit category, the objects here and the objects here become equal. So what's happened, well, isomorphic, if you will. What's happened is that I keep one copy of every module. I also have a copy of the shifts of the projectives, so sigma P1 and sigma P2. And then if I go more to the right, I go back here, yes? So it's as if I had an infinite ribbon, and then I close it up, yes? And this is the cluster category. So the two So you don't get back to the projectives. That's the beauty of it, because I could have, let me make this more so that it resembles what I'm actually doing. So I'm taking the quotient with respect to the action of this functor, yes, or maybe, so I apply the shift first, the suspension functor first, and then the inverse of tau. So what happens? So let me start here. I apply first the suspension, so I get to this white line, yes, that's the projectives. And then I apply tau minus 1. This line is equal to the projectives. These are not the shifted projectives, yes? These are the shifted projectives to which I apply tau minus 1. So if I start again, what happens? I apply the suspension, so I have this is my second line here, and then I apply tau minus 1, so the third line here is equal to the second here, is equal to the first here, is equal to the minus first on the next segment here, and so on. Yes. But they do have a kind of a specific role, because I remember the information of the module category. Yes. So what I write here, this sounds very bizarre, but what I mean here is that all the red lines that you see become equal in the cluster category. And so in some sense, the cluster category, what does it look like? White color. So the cluster category looks like this now. So I have these bits of projectives, I go to the tubes, and then I go back to where I were, yes? So I'm going to draw this in this way instead. I have the tubes somewhere, and if I go left of the tubes, let's imagine you're in one of those old video games where when you get to the end of the screen, you just end back here, yes? So what I have is something infinite like this. And somewhere in here, I have this red line. But it doesn't really matter. That's what Laurent's comments was about, yes? Since this band is infinite on both sides, any slice like this can play this role. Yes? But I just remember where it is, because it's convenient. So, I should roll it up. Well, yes. I mean, you should imagine that this goes here as well, yes? That's what you meant, I guess. Okay? So that's a very detailed description of everything in the cluster category of the Kronecker quiver. So what should you remember from this in this example? What is general in what we've seen? Well, in the cluster category, yes, you can view this part here as a kind of fundamental domain for the cluster category inside of the derived category. So in the cluster category, what are the indecomposables? Well, you have as many of them as you had indecomposable modules, plus one copy of every shifted or suspended indecomposable projective module. Yes. So you have as many indecomposables as you had indecomposable representations, plus n, where n is the number of vertices of your quiver. And then it wraps around, yes? So this is something to remember. Yes? In some cases, yes, not for the Kronecker quiver. Yes. Okay. So as we saw in the example of type A2 that was done by Bernhard in the previous lecture, indeed, when you glued it together, you needed to twist it, so you had more of a Möbius strip. For this thing, even though it's infinite, it doesn't make so much sense, but imagine it was smooth. Yes, I don't twist it, I get a real cylinder. It's in the way that I've drawn it, I don't twist it, yes? And if you were to draw it in such a way that you would need to twist it, I would disagree with your drawing, I think. But yes. Well, it comes from this action here, yes? This action means that for any, what I want is that in CQ, I want that every object X becomes isomorphic. So what I draw here is with my hands. It's not rigorous, it's just the idea of what's going on. I want that X becomes isomorphic to this functor applied to X. So the projectives become isomorphic to themselves, to which I apply this functor. Yes? Everything in between, it's not clear. You have to prove it, that's true. But anything in between remains not isomorphic, not pairwise isomorphic. So here, in my example, I had P1, oh, was it P1? Yeah. P1 and P2. And two morphisms like this. This is the red line. Yeah. So here on the white line here, that's the suspension of P1 going to the suspension of P2. And then on the red line here, it's the suspension composed with the inverse of tau applied to P1 goes to the same functor applied to P2. But this I declare, by taking this orbit category, I declare that this becomes isomorphic to this. I have infinitely many, because as you see, in the middle, I have infinitely many tubes. And this component is infinite. This component is infinite as well. So I still have at least as many indecomposable as there were in my module category. Here, yes. So the ones here are precisely the ones here, which also turn out to be the ones here. Now, if I go one step or a few steps to the right, like this guy, call it X, it's going to be here, call it X. Or maybe I go to the left, maybe this guy, call it Y. It means I go to the left here of the red stripe, call it Y, and so on. So you really have a correspondence between the two pictures. Oh, I should say that's true. On the tubes, tau is just the identity. So on the tubes. That's a good point. Any more questions? Yes? Yes? To do what? I apologize. I don't want to think of this, I mean, I don't want to think of this as a surface. It's a useful image, but it's really something discrete, yes. But I mean, if you start with any quiver, it's true that in the bounded derived category, what you have is a copy of the module category, and next to it, it's suspension, and next to it, the next suspension, and so on. So you can play the same little game. The question is now, in the module category, can you describe what's happening here? You can to some extent. That there's going to be tubes, there's going to be something that look like planes, and so on. But it's difficult to give a complete description. I don't think that was the question. But yes. Yes. You will have a connected component which looks like Z many components of your quiver, copies of your quiver. So a ZQ component. Yes. But outside of this, hard to say. Yes. For a general quiver, the module category is wild, so it's difficult to give a classification. Well, impossible to give a classification. Yes. There's no topology. It's just an image. Yes. And it's that. Yes. Any other question? Okay. So this example is one that is, it's a good idea to play with it and to make sure that we can do computations with the Kronecker quiver. It will serve us as a running example throughout the 4 lectures. Now, one thing I want to mention, it's going to be useful a bit later. Let me write this as a proposition. We can make, that was an observation here, that the indecomposables in the cluster category are in bijection with the indecomposables of the module category plus n shifted projectives. And you can make this a little more precise as follows. So let Q be any acyclic quiver. Then if you look at the following functor that takes an object in the cluster category and sends it to so if I could take an object X, I want to send it to the space of morphisms from the algebra viewed as an object of the cluster category. This is the sum, the direct sum of the indecomposable projective modules to X. Now this is a module, a right module over the endomorphism algebra of KQ, and this one is isomorphic to KQ itself. So I end up in the module category of KQ. That's a functor. I'll call it F. And this functor induces an equivalence of k-linear categories in the following way. If you take the category, the cluster category CQ, and you mod out by the ideal of all morphisms that factor through direct sums of KQ, through the projectives. Shifted projectives, and you get an equivalence of categories. And this here, as I said, is the ideal of morphisms factoring through an object which is a suspension of a projective module. So in this picture, I said you could view the cluster category as being the module category with n additional objects. The more correct way to state this is you can view the module category as being the cluster category where you kill n objects, indecomposable objects. Yes. So the module category is a factor of the cluster category. It's still useful to remember that it's almost like the module category where there are n additional indecomposable objects. Okay. So that's with the example done in detail. Now, in order to talk about indices, I need to talk a bit more about projective modules and projective resolutions. Well, projective presentations, to be exact. So for a short while, I'm leaving the realm of cluster categories, and I'll be staying inside module categories for the moment. But this will be applied to cluster categories after that. So you've seen already in Laurent's talk what a projective module is. Let me remind you what the definition is. So if I have any finite dimensional K algebra, I could be more general than that, but I don't want to. Then a projective module is a module P such that the following is true. A projective A module is a module P such that the following is true. Whenever you have a surjection between two A modules, so for all surjection like this, and any morphism from P to the last module here there exists a lift to M such that the triangle commutes. Laurent defined projective modules, I think, as saying that a certain X group vanishes. As an exercise, you can prove that this is equivalent. So, of course, an example, the algebra A viewed as an A module is always projective. Yes. A viewed as a right A module is projective. Because whenever you have a surjection between two A modules, if you have a map from A to N, a morphism from A to N is completely determined by where 1 is sent. So if 1 is sent to small n, this map is surjective, so there's a small m that is sent to small n via this map. And all you need to do is define the morphism from A to M that sends 1 to small m. And this diagram commutes. So A is projective. Now, I won't be needing general results about projective modules. I will be needing practical ones. So let me mention some of the properties of projective modules. The first one I want to mention is that direct sums of projective modules are projective modules, and direct summands of projective modules are projective modules as well. So if you have a family of modules then the direct sum of this family is projective if and only if all the modules in this family are projective. So that's one thing. So in particular, since we know that A is projective, then any direct summand of A is also projective. And using this, you can find all indecomposable projective because a module is projective if and only if it is a direct summand of a free module. So thanks to the Kohlschmidt theorem, an indecomposable projective is a direct summand of a free module of rank 1. So if you want to know a complete list of indecomposable projective modules up to isomorphism, all you need to do is take your algebra A and decompose it into indecomposable direct summands. Okay? And maybe something even more practical. In the case where your algebra is a path algebra of a quiver, you can actually compute all the indecomposable projectives. So let Q be any acyclic quiver. And I will be working over the path algebra of Q. So modules over KQ are representations over the opposite quiver. Okay. E1 up to En, the lazy path, or the path of length 0, associated to vertices 1 up to N. Then the indecomposable projectives are given in the following way. So I'll call them P1 up to Pn. I should say up to isomorphism. And Pi is the right module given by KQ multiplied on the left by EI. This is obviously a right module, and it's also projective, and it turns out to be indecomposable. And this is a complete list of all indecomposables. Now, if you want to view this as a set, it's the set of linear combinations of paths in Q that end at the vertex I. Remember that I compose my arrows as morphisms from right to left. So I is the endpoint of my path. So maybe we can look at an example. Well, we've already seen what happens for the Kronecker quiver, but let's maybe look at what happens really. So Q is the Kronecker quiver. I'm looking at KQ module. That means I'm looking at representations of the opposite quiver like this. So I want to look at path. I want to compute P1. So I want to look at paths that end in 1 in Q. That means I'm looking at paths that start in 1 in Q op. Yes? And what is here, it's going to be, on the first vertex, is going to be the vector space of paths that go from 1 to 1 in Q op. And the second vertex is going to be the vector space of paths going from 1 to 2 in Q op. So in the first case, I have only one path from 1 to 1, that's the lazy path. And in the second case, I have exactly zero morphisms from 1 to path from 1 to 2 in Q up. So I have 0 here. So we've already said that this is P1. But now maybe we know why. What is P2? I have to look at path going from 2 to somewhere. Yes? So what are path going from 2 to 1? I have 2, 1 for every arrow. So I have these of 2 here. And what are path going from 2 to 2? I have only 1, the lazy path. So I have 1 copy here. And what are the arrows? The arrows correspond to composing with each of these arrows. So I have path from 2 to 2 here. If I compose with the arrow on top, I get a path from 2 to 1. If I compose with the arrow at the bottom, I get another path from 2 to 1. Yes? So if I choose my basis accordingly, I can write my morphism like this. If you want to get acquainted with the computation of projective modules, you can do this as an exercise. Take Q to be this quiver with 3 vertices and 4 arrows, and you can compute all 3 indecomposable projectives. You compute them as representations, and they are as follows. And I'm not giving you the morphisms, but you can compute them for yourself. Now, what are projective modules good for? Loosely speaking, they are good for describing modules by giving generators and relations. And one way to say this would be the following, which I write as a theorem. If I take any A module M, then there is a surjection from a projective module onto M. There exists a surjective morphism P goes into M with P projective. And to see why this is true, take any set of generators of... I should write this in English, you're right. I don't think, it's just a reflex, yeah. It's like putting a square at the end of a proof. I mean, the proof starts with them and ends with a square. Okay, so what do? If you choose any set of generators for M, so if, say, Mi is a set of generators for M as an A module, such a set exists, yes? If you want to be very crude, you can say that M, big M itself, is a set of generators for M. It's not a very useful set of generators, but it is one. So such a set exists. And with such a set, you can define a morphism. So I'll take a direct sum of several copies of I, as many copies as there are generators in my set, and I'll send this to M in the following way. If I have here an I tuple of elements in A, this is a direct sum, so this I tuple is finitely supported. So there's 0 almost everywhere. And I send it to the linear combination of the elements in my set of generators with scalars AI. Now this is surjective, and it's also a morphism of A modules by definition. Oh, my modules are on the right. So it should be like this. Yeah. Maybe I should write CQFD. You have a question? I'm not asking that I is finite, but of course if you add some hypotheses, like if you say that M is finite dimensional over K, then instead of any set of generators, you could choose a basis over K. It would be a finite set, and this would still work. So this would be a finitely generated projective module. So maybe I should write this as a remark. So if M is finite dimensional over K, then this projective module can also be taken to be finite dimensional over K. Yes? Finitely many of them are non-zero, yes. Yes. I mean, it's part of the I haven't written it down because it's part of the definition of a direct sum, but this is finitely supported. Otherwise, of course, this map doesn't make sense because infinite sums are not defined in a module. Okay, so if you believe that, well, we know it, we've proved it. If you believe that any module can have any finite dimensional module can have a finite set of generators, and this is true, it's finite dimensional, just take a K basis, then always have a surjection from a finite dimensional projective onto M. In fact, in our proof, the projective was free, but we don't need that. Yes, we can be a bit finer than that. And the question is, in some sense, one question you could ask, loosely speaking, is if you look at all the sets of generators for your module M, is there a smaller one, or a smallest one? Yes. Is there one that contains as little generators as possible? So if you're working over vector spaces, you're just talking about the basis, right? There exists the smallest set of generators, it's a basis, all bases have the same cardinal, and so on and so on. You'd like to do this for modules as well, yes? Now, what you need to do is look at different projective presentations, yes? Different surjections from a projective, yes? You see in this proof that the surjection from a projective is pretty much the same as a set of generator from M. And you will try to see what is the smallest surjection that you can get from a projective. Now, nothing of this made sense. Let's make sense out of it. So that's a definition. What you would like to be a smallest surjection from a projective is what we will call a projective cover. So a surjective morphism P to M, call it pi, with P projective, we say that this is a projective cover of M. If the following is satisfied. Suppose that you have another surjection onto M from a projective. Surjection pi prime with Q projective. Then this surjection factors here, because P is projective and Q is projective, sorry. So by definition, this factors here, and this will need to factor through a surjection. And in fact, this surjection will be a retraction. So there exists a retraction that makes the diagram commute. So it's a surjective morphism from a projective to a projective. This means that you can view P as a direct summand of Q. Oh, okay. thank you for that. This is a split epimorphism. So in particular, Q is isomorphic to a, sorry, P is isomorphic to a direct summand of Q. So why is it the smallest possible projection from a projective module onto M? If you have any other such projection, then P is a direct summand of Q. Yes. Now the result, of course, which I will not prove, we'll just assume it, is that for any finite dimensional module over a finite dimensional algebra, projective covers exist and they are unique up to isomorphism. So let A be a finite dimensional K algebra and M be a finite dimensional A module, then M admits a projective cover unique up to isomorphism. Uniqueness is easy, existence is the real theorem. And now this is all abstract, but what we need to do is to be able to compute this, for path algebras at least. So let's view some examples. So let's take the Kronecker quiver. We're getting to know this quiver a little bit, yes? So let's do some more things about it. We know what the projective representations are, the representations of the opposite quiver. So P1 is one-dimensional, P2 has dimension vector 2, 1. So let's compute projective covers of the simple modules. So what's the projective cover of the simple module S1? Well, S1 is the projective, is its own projective cover. You cannot find any smaller than that. What about S2? S2 is the representation of dimension vector 0, 1. The simple at the vertex 2. There is an obvious projection from P2 to S2. Yes, let me write it down. Maybe I want to write down my representations vertically now. I hope you won't mind, because I want my exact sequences to be horizontal. And I claim that there's a projection from P2 to S2. So P2 is written like this. Of course, these two maps are 0. And you just need to find two morphisms like this that are such that the two squares in this picture commute, yes? If you use the horizontal arrow on top and then the left vertical arrow, it should be the same as using the left vertical arrow and then this morphism. Of course, here I have no choice. This is the zero morphism. And on top, I claim that if you put the identity, then this works. This is not so hard to see, right? Because if you do this, well, you compose with 0 either way. So this is always 0. And if you do this, well, you compose with 0 either way. So this is always 0 as well. Yes. This is a natural projection. So this is the projective cover of S2. Again, you cannot find any smaller than P2. P2 is indecomposable. As an exercise, if you take the following module of dimension vector 3, 2, that's an indecomposable module. I'm not writing down what the morphisms are for the arrows, but if you remember the classification of indecomposables for the Kronecker, there was only one with this dimension vector. So you can find it back if you have written it down earlier. And I claim that the projective cover of M looks like this. There is a surjection from 2 copies of P2. So as an exercise, you can try to find this surjection. And once you've got it, how can you prove that it's the projective cover? Why is it minimal? You know? Well, if it wasn't minimal, then the minimal one would be a direct summand. But if you're a direct summand that is strictly contained, your dimension vector is not big enough to have a surjection onto M. So that's not possible. Yeah. So all you need to find is this morphism. Okay. Then I just have enough time to define a projective presentation for a module. Maybe before I give the definition, let's see what we are going to do. So, orange is not rigorous, it's just a picture. If you have a module M, you can find its projective cover. You can take the kernel of this map. So maybe I call it pi. So you can take the kernel of pi. That's a module, finite dimensional. It has a projective cover. So maybe this is P0, this is going to be P1. So pi 0, pi 1. Pi 1 is the projective cover of the kernel of pi 0. If I compose these two maps, I get an exact sequence. And what I've just built here is what we will call a minimal projective presentation of M. How should you think of that? P0 is somehow gives you a set of generators for M. Yes, I think it's still on the board. This is how we prove the existence of a surjection from a projective to M. So here it gives you information about the generators of M. If you take the kernel, it gives you information on the relations between these generators. Yes? And if you take a set of generators for the space of relations between generators of M, you get the projective cover here. So P0 encodes information about generators of M, P1 encodes information about relations between the generators of M. So we call this a projective presentation. If you do some group theory, maybe you've seen groups defined by generators and relations. We call this a presentation of a group. So the word projective presentation here is used in the same sense. So I just have time to give the definition now. A projective presentation of M is an exact sequence of the form P1 goes to P0 via pi1 goes to M via pi0, and I want this to be a surjection, so I want this to be exact with P1 and P0 projective. And this projective presentation is minimal if, well, pi0 and pi1 are minimal in some sense. So if pi0 is a projective cover of M and pi1 is a projective cover of the kernel of pi0. So since projective covers exist, minimal projective presentation exists as well, and they are unique up to isomorphism. Now, what I will do tomorrow in my lecture is I will take all these notions of projective presentations. These are in the module category, but we're interested in the cluster category, which is slightly bigger. Yes, the module category is a quotient of the cluster category. So what we'll do is take these notions and lift them to the cluster category. So it doesn't make sense to define projective objects in the cluster category, but it will make sense to somehow define something similar to projective presentations in any case. And this will allow us to do some computations. But that's for tomorrow. Thank you very much.
Thank you, Pierre-Guy, for your excellent and wonderful talk, which is, has a more broad overview of this subject, as in more details also. So, are there any questions?
Well, what I mean is finite dimensional over the base field K, because an A module is in particular a K vector space. So I mean finite dimensional over there. It happens that since my algebras are finite dimensional over K, then finitely generated and finite dimensional are the same thing in my case. You could continue, yes. I've only defined P0 and P1, but take the kernel of pi1, take a projective cover, you get P2. Take the kernel of pi, and so on. You get a projective resolution. This can be infinite. You can always define it. Just one. Sorry? I mean, you don't need it to be a projective cover at every step. Yes, so it doesn't have to be minimal in some sense. But what I will use is only minimal projective presentation. So it's important for me that minimal resolutions do exist. Sorry? Yeah, but I mean, let's not go into that. I mean exactly. So so here, if pi0 is a projective cover of M, then pi0 represents a minimal number of generators for M. And if pi1 is a projective cover of the kernel of pi0, then P1 represents a minimal number of relations between the generators, yes. That's equivalent to the definition I've given in my context, yes. I work over a finite dimensional algebra over a field.
Okay, any more questions? In that case, let's thank the speaker again.
Thank you.